Hello, I'm Dantani, the captain of team DJS Antariksh, the official Martian rover team of Dwarkadaas J. Sanghvi College of Engineering, Mumbai, India. This year, we are thrilled to participate in the European Rover Challenge 2026 with our rover Avyaan. Our team was founded in 2019 with the motto to decipher unimaginable. Today, we bring together 60 passionate students across 5 key departments: mechanical, electronics, coding, science, and marketing and management. Our team follows a vertical hierarchical structure wherein the team captain provides strategic direction, guiding the team towards its goal. The vice captains and the team managers support coordination by managing timelines and overseeing administrative processes. The integrations head manage inventory and facilitate interdepartmental coordination. Each department is led by the department heads whose expertise in the domain ensures subsystem development.
Hello, I am Palash Dhabalia, the mechanical head at DJS Antariksh. The mechanical department handles designing, manufacturing and assembly of the rover with a focus on developing components which work efficiently under varied terrains.
I am Ishan Amdekar, one of the electronics heads of Team DJS Antariksh. The electronics department oversees power distribution across subsystems and processes collected data from the sensor and ensures reliable communication between the rover and the base station.
I am Harsh Vasa, the coding head of our team. The coding department manages the complete software stack of the rover and it oversees the development and implementation of its autonomous navigation and robotic arm operations.
I am Shreya Dalvi, the science head of DJS Antariksh. The science department leads research and analysis by taking data from exploration, astrobiology and sampling and converting it into useful insights that support the mission objectives.
I am Shan Upadhyay, one of the marketing and management head responsible for securing resources for supporting our project and also overseeing allocation of funds and logistics. We also lead the team's branding by managing our social media and participating in outreach programs.
Our team DJS Antariksh was founded with the primary aim of competing in the European Rover Challenge. Over time, we have successfully qualified and competed internationally, gaining experience through every iteration. The ERC is a leading Martian rover competition where teams are evaluated not just on rover performance, but also on documentation, mission planning, and outreach. This makes it a multidisciplinary effort where every department plays a key role in the final outcome. For us, the ERC is where everything started, and it continues to shape the way we approach engineering problems through iterative design, testing, and constant refinement. Every year brings with it new challenges, pushing us to rethink and improve our systems, making it a crucial part of our growth as a team.
The mechanical department has redesigned the robotic arm to a 5DOF configuration, eliminating the redundant 4th joint from the previous iteration to improve efficiency. The base joint employs a worm gear assembly, while the first and second revolute joints utilize inverted cycloidal gearboxes to minimize backlash and improve accuracy. The bevel gear system comprises 4 bevel gears, enabling a compact arrangement, while herringbone gears are incorporated to mitigate misalignment. A new robotic arm has been developed with a 5DOF configuration, incorporating high-precision servo motors that are directly coupled to each joint, providing smoother motion suitable for autonomous operation. The structure is 3D printed using ABS, while carbon fiber tubes are integrated to enhance strength. The chassis is constructed using hollow aluminium square pipes, replacing the V-slot aluminium extrusion profiles to reduce weight and improve durability. It houses all onboard subsystems including the robotic arm, collection mechanism, spectrometer, antenna and cameras, ensuring efficient operation. A double rocker suspension system with a 4-wheel independent steering mechanism has been developed, incorporating a worm gear drivetrain. This configuration facilitates advanced maneuvers such as double Ackermann steering, crabbing and spot turning while maintaining a ground clearance of 300 mm and enabling the rover to climb inclines of up to 60 degrees. The wheels retain their previous design with a wave-serrated tread pattern, enhancing traction on loose soil surfaces, while a thunderstrip pattern provides effective shock absorption capabilities. The wheel is manufactured using TPU through FDM to enhance flexibility.
The electronics department oversees the telemetry, data acquisition, actuation, and power distribution of the rover. All electronic components are housed within an acrylic enclosure, providing protection from harsh environmental factors. The rover is powered by 6 24-volt LiPo batteries connected in parallel with a power distributed to custom-designed PCBs featuring DC-to-DC buck converters. The actuation system consists of navigation, a robotic arm, and collection mechanism. The navigation system incorporates BLDC motors for independent steering, along with high-torque servo motors for traversing. The arm and collection mechanism also use servo motors, all equipped with rotary encoders to provide precise feedback. The data acquisition subsystem processes inputs from sensors along with camera feeds using the onboard microcomputer. For safety, a dual kill switch system is implemented where the main switch halts all rover operations, while the secondary switch disables only actuation while maintaining communication and onboard processing. The telemetry system uses a 13 dBi omnidirectional antenna on the rover and a 19 dBi sector antenna at the base station, communicating via Rocket M5 modules over the 5 GHz band to ensure stable communication even in non-line of sight conditions. Additionally, a 5.8 GHz high band operating on the TS835 module will be used for analog video transmission in case of failure in primary camera feed.
For manual operations this year, all onboard camera feeds are handled using a G-streamer-based pipeline, reducing CPU usage and bandwidth consumption. For autonomous navigation, the Z2i camera is used to generate a 3D point cloud, which is then converted into local and global cosmos. For localization, various inputs including visual odometry from RTAM map, wheel odometry, IMU data, and pose estimates from Aruko marker detection are fused using unsalted Kalman filter to obtain the rover's pose estimate. The cost map and the pose estimates are used by NAV2 stack for path planning and execution, where the theta star acts as the global planner and regulated pure pursuit acts as a local control. Behavior trees are used to ensure smooth execution and recovery. The autonomous stack has been tested in simulation to validate the algorithms and ensure reliable operation. The autonomous operation of the robotic arm utilizes Aruko marker detection to estimate the panel pose, alongside a YOLO-based object detection model is used to identify the elements of the panel. Based on this and the current arm position, the target pose is determined. Move It 2 then handles motion planning and execution, where IKFast computes the joint configuration and OMPL generates a smooth, collision-free path. A diffusion-based vision language action model takes the task instructions, visual input, and arms joint state to follow task instructions and operate on the panel.
The drone is a 10-inch hybrid X-frame quadcopter built using carbon fiber arm links and 3D printed ABS body. The onboard electronic components are mounted on custom design support to maintain proper weight distribution and to reduce aerodynamic drag. The system is powered by a 4S 6200 mAh LiPo battery supported by a capacitor to reduce voltage spikes and an integrated BEC to provide stable power to the onboard electronics. The avionics system is based on the SpeedyB flight controller integrated with GPS and optical flow sensor for accurate navigation. A Raspberry Pi 4 Model B is used for onboard processing and higher level operation. The drone utilizes a 2.4 GHz communication link for flight control and a 433 MHz telemetry link for MAVLink based communication, enabling reliable bidirectional data exchange with the ground station.
For autonomy, probe detection is performed using the YOLO V8N model on the monocular RGB camera feed. Drone coordinates are estimated in MATLAB using the camera's field of view and altitude. Landing is guided by Aruko-based pose estimation with positional corrections sent over MAVLink, and an auto-land is triggered on battery or communication failure. A manual override on the RC controller allows the operator to instantly switch to manual mode. The overall mission logic is implemented as a simulating state machine, handling takeoff, detection, and landing.
The science department uses tools like JMAS and Google Earth Pro to analyze Heliospaniacia, identifying a suitable landing site and regions of scientific interest. Based on the Marsyard, a falsifiable hypothesis is formulated, which is invalidated using an auger penetrometer that is being developed to measure the penetration resistance and auger index, enabling subsurface stratigraphy mapping, while a custom-built Raman spectrometer with a Cherney Turner configuration helps in analyzing soil composition. A digital microscope captures high-resolution terrain imagery supported by a soil multiparameter and a BME 680 sensor for subsurface and atmospheric monitoring. For sampling, a scoop and deflector will be used to collect regolith and rock samples, each deposited into separate containers equipped with calibrated load cells for precise weight measurement, while a third container will store subsurface samples extracted beyond 30 cm by a centrally placed aluminum auger driven by a high-torque motor and reinforced with support rods for stability. For Astro-bio, a pH sensor on the end effector measures sample's pH, while a peristaltic pump transfers it into a sealed container with a one-way valve preventing contamination and leakage. The modular end effector consists of two moving fingers with tapered ends actuated using a lead screw mechanism, while a guide rod has been integrated to provide additional stability. Designed for autonomous operations, the end effector of the newly developed arm incorporates a rack and pinion mechanism driven by a waveshare motor. The fingers have a serrated design, enabling it to operate on switches, locks and plugs for the maintenance task.
We're thankful to the European Rover Challenge for this incredible opportunity. We're also grateful to our college and sponsors for helping us achieve our goals, and to our mentors for their constant guidance and support.